Morning, everyone. Anybody have any questions before we get started? I'm going to try to make sure I can connect with my iPad real quick.
I had a question on one of the homeworks.
Okay, go for it.
So on I think it's conceptual homework, or maybe it's homework number 2, the one that's due on Tuesday.
Uh-huh.
There's it's for number 3, it's this crossing a river problem.
Right.
Um I get what it's trying to say. Like I understand it conceptually, but the way it's trying to ask for me to represent the math is not the same way I do it. So I'm finding it hard to enter the correct answer in the way they want it, even though I understand it conceptually, if that makes sense.
Gotcha. Yeah, I sort of remember that problem. Let me see if I can pull it up real quick and get a look at it since I haven't seen it for a little while, but I definitely remember it. Go in there now. Let more students in. Got about a minute before class starts. Mastering assignments.
It's chapter 3, homework part 2, question 3.
Oh, gotcha. I see. View assignment. Projectile motion, conceptual, delivering, kinematic. And which you said it's problem which one?
Number 3, the crossing the river.
Oh, yeah, I see it now. Crossing a river. Gotcha. I'm pulling that up to look at it right now. I'll read it aloud for everyone. It says a swimmer wants to cross a river from point A to point B. As shown in the figure, the distance D1, which is directly across from A, across the river, is 200 meters. The distance D2, which is along the other shoreline from basically C to B, is 150 meters, and the speed VR of the current in the river is 5 kilometers per hour. Suppose a swimmer's velocity relative to the water makes an angle of theta equals 45 degrees with the line A to C, okay, as indicated. To swim directly from A to B, what speed US relative to the water should the swimmer have? Okay. So what they're asking here is, let me draw a diagram so I can give you an idea of what's going on. And this will help everybody. It's sort of more in line with what we're doing tonight anyways, which is starting to cover vectors. So we have a river, if you will, just like this and this. This distance D1 is equal to 200 meters. And
We can't see your screen.
okay, thank you. Yeah, let me do that. I forgot I'd closed it out already. There, there. Now it might take a little bit for it to come in, but it should come in pretty soon. And we got the stream is running this way. It's running to the right in my diagram, which hopefully you'll see pretty soon. And that's the velocity of the river with respect to the earth, say. And that is 5 kilometers per hour. Notice I changed the terminology a little bit. They just called it V sub R. I'm calling it V sub RE because it's supposed to be the velocity of the river relative to the earth. Why is this not pulling up? It says it's trying, so at least it's attempting to do, right? There we go. So now we have that. Now, what we're trying to do is, this is point A, and I've got that stream side is kind of wavy. It's not supposed to be wavy, so y'all can just ignore that. This is point C, and down here is point B. Okay. I got another person coming in late. Let's do that. Okay, and it says this distance right here is D2, and D2 is equal to 150 meters. And so they're sort of drawing this line right here and drawing this line right here. And then they're drawing sort of a dash line this way. They're also showing the swimmer swimming with an angle theta, and they're suggesting theta is equal to 45 degrees. So they said to swim directly from A to B, what speed US relative to the water should the swimmer have? So what they want to know is US, and that's the velocity of the swimmer relative to the river. So I'll call it USR. And they're going to say equals question mark. All right. As I said here, this one is the velocity of the river as seen by the earth, and the velocity of the swimmer as seen by the earth is equal to the velocity of the swimmer as seen by something plus the velocity of that same something as seen by earth. So what we do have is a RE, so I can say the swimmer relative to the river, and that fixes it. So that's our addition of velocities formula that we want. But they're specifically asking for USR, so we don't necessarily want to know the velocity of the swimmer with respect to the earth, not in part A anyways. So I'm just letting you know that's what that is. But what they're trying to suggest, if you want the swimmer to swim directly from A to B, what speed US relative to water should a swimmer have? So in this case, they're swimming at 45 degrees, and what you need is 45 degrees times cosine of the velocity. You need that to give you exactly the right amount of time for the object to go from A to C. But in that time, it's got to go a distance D2. So what do I mean by that? I mean, here's my solution. So what we're saying is D2, which equals 150 meters, that's got to be the velocity of the swimmer relative to the river times the time taken. So in other words, if you multiply distance time, velocity times time in the what I'll call X direction, then if I multiply that velocity times time, that'll give me a distance. But I also need that D1, which is equal to 200 meters. I need that to take the same amount of time, and that is the velocity of the swimmer with respect to the river in the Y direction times T. Okay, so you can look at it this way. You can say, all right, this is 150 meters equals USR sub X T, and 200 meters USR Y times T. This will be equation 1, and this will be equation 2. I'll take 2 and divide it by 1. And when I do that, I get 200 meters over 150 meters is equal to USR Y over USR X, which is actually equal to, in this case, it turns out to be the tangent of the velocity of the swimmer with respect to the river, because the Y component over the X component is that. Now that's the velocity relative to the river, but that helps us a lot. So we can see, for instance, that 200 divided by 150 would be 4/3. And that suggests, in fact, that the angle, which I'll call phi, is actually equal to 53.1 degrees. So that's the velocity basically that it actually has to travel relative to the stream, which is going to the right. But that's part of it that can help us. So what we want to know is water, what velocity does it have to have? So we have that part. Now swim directly from A to B. It's weird that they asked for A to B instead of from A to C. Uh,
Didn't they say that theta is 45 though? Or where does that plug in, I guess?
Yeah, so that's what's going on here is we're using a velocity of the swimmer relative to the river, and the velocity of the swimmer relative to the river. Sorry, I'm having a hard time saying river. Is actually equal to the velocity of the swimmer with respect to the earth minus the velocity of the river with respect to the earth. So I'm just basically solving that equation that I just put a star by to find out what USR is, because USR is really what we're needing. What we see is the ratio of the y component to the x component of those velocities has to be 4:3. And though this 45-degree angle is what the velocity has to be relative to that line across the river, that's not necessarily the same as this angle phi. So that's why I don't get the same angle for that. Now, what I can do is I can say, now that I have, well, no, I can't do that because I don't have the time yet. But if I say that the velocity of the river, or excuse me, the velocity of the swimmer times cosine 45 degrees, that's got to be the component in this direction, like that. So that is USR cosine 45 degrees. That has to be equal to the D1, or that has to be equal to what we call 200 meters. Darn it. And then the velocity U sub R times the sine of 45 degrees. That one actually has to not completely cancel out the velocity, but it has to be times time. Oops, I left that completely out. That's not very good. So let me times this, times time, let me times this, times time. This one's going to be the 200 meters, and this one's going to be the 150 meters. That's still not working yet. So let me think of another way. Is this the only part, or did they give you another part when this one's done?
So I'm assuming you unlock another part, but as the first part is solving for the velocity of the swimmer. I've tried doing it as like a vector formula, like finding a vector of the swimmer in that direction and then solving for the velocity, like leaving that as my leaving
Right,
that as my unsolved and then using the vector of the stream going in like the zero direction and going in the east direction as its own vector, then adding those together. But I
right.
wasn't sure if I was supposed to create like a unit vector and then the time will just be plugged in to get to your A to B, which is like 250 meters is your A to B if you solve it.
Gotcha.
But it wouldn't give you like it would give you I solved for velocity, it gave me like 1.4 or something, which could make sense for swimming in the opposite direction at 1.4, but you're going forward like positive y, but that
Okay,
could
so you're
cancel out,
saying
you know what
the
I mean?
leftmost velocity, like the velocity to the left, is 1.4, and of course that's being canceled out by the 5 kilometers per hour. Is that the figure you got?
That's what I got, but I wasn't sure if the math is right. And it seemed like it was kind of solving for like a unit vector that you could scale up with time, that would give you the
Right.
time to get to 250. But I wasn't sure. And when I looked at the hints, it was solving like if you look at the hints, it has you solve for you end up getting like d1 over velocity swimmer times cosine theta, and then d2 is velocity river minus velocity swimmer sine theta, and then you have those equal each other. But that's not the way I did it, so I was trying to
Gotcha.
figure out the right way to do it because I feel like my answer might have been wrong.
Gotcha. It sounded the 141, that sounded like a reasonable answer. So I'm looking now for a different way. So what I just did is I said the velocity of the swimmer with respect to Earth. So let's sort of ignore this stuff that I did right here. It's probably going to work out to where we'll see it coming back into play. But what I'm doing is I'm doing the velocity of the swimmer with respect to Earth is equal to the velocity of the swimmer with respect to the river plus the velocity of the river with respect to the Earth. Now we know what the velocity of the river with respect to Earth is. That is 5 kilometers per hour. And you'd pretty much call that in the I hat direction. So that would be acceptable. And then the velocity of the swimmer with respect to the river. Now that is a little bit weird part, but the velocity of the swimmer with respect to the river is going to be an x component. It's in fact going to be negative USR times cosine, times sine times the sine of 45 degrees, because that's just taking into account that they told us the angle was 45 degrees, and that would be in the I hat direction. And then the velocity of the swimmer with respect to the river in the y hat direction is just going to be the velocity in the y direction, which would be positive USR cosine 45. And that would be in the j hat direction, which is I'm basically saying my coordinate system looks like this. This is the positive x, this is the positive y. So that should be it. What we do know is they didn't give us any maximum speeds or anything like that. Okay, so I can say that this is going to be negative USR. Of course, the sine of 45 is square root 2 over 2. And then that'll be I hat plus US sub R again times the square root 2 over 2, only this time it'll be positive. There's your J hat. And if you, now that you know what the Y component is, you can use that to figure out how long it's going to have to travel. So we can now say we can now say USR times the square root 2 over 2. That's really the component of velocity going directly across the river. If you multiply that by time, then that should give you the full 200 meters. So if we do that, we can get 200 times 2 and then divided by the square root of 2. And that gives me 200, that gives me USR times T is equal to 282.8, carrying one extra sig fig, and that is meters. Now, that almost gets us, and we can say T is in fact equal to 282.8 meters divided by USR. So that is one unknown that we sort of gotten a value for. Now, what I also need is I need that component of velocity that is parallel to the stream, the one that goes to the left. I need that to take the same amount of time to go a distance of 150 meters. So now what I'm going to do is I'm going to say USR. Now that's the velocity to the left, but the total velocity, of course, is going to be that minus, or I should say 5 kilometers per hour minus that, because it's trying to fight by going to the left, but the 5 is constantly pushing it to the right. So I'm going to say that's the total velocity. That's the total velocity in the right direction, 5 kilometers per hour minus USR cosine 45 degrees. Well, actually, I should say in this case, it's sine 45 degrees. So that's the total velocity. That multiplied by time is supposed to give us 150 meters. But now I can take this time and plug it in there, and that's going to give me 5, let's say kph minus USR times the square root 2 over 2. All that times 282.8 meters over USR has got to equal 150 meters. Now let's see what we can do with that. We get 282 times 5. And that's sort of a mixed unit, so that's something I got to be careful with, but I'm going to watch it right now. 282, yeah, I guess I could convert that to kilometers, then it would work a little better. So, in fact, yeah, let's do that just to watch the units. This is going to be 0.2828 kilometers. So using that, that'll automatically work out a little better with this 5. So if I multiply 5 times 0.282, I get 1.414, which is way more sig figs than I wanted, but that's kilometers squared because it's kilometers per hour times kilometers, and then it's over hours times USR. So that's just distributing to this first term. And the other one, the USR, is going to cancel out here. So in this case, I'm going to get the square root of 2 over 2. So square root 2 divided by 2, that's 0.707. And now I'm going to multiply that by 0.282. And that's 0.2828 again. And that gives me essentially 0.2000. And that's going to be kilometers. Yeah, I think that just turns out to be kilometers, because when I take the kilometers squared and divide it by kilometers per hour, that becomes just plain hours. So that seems to work okay. And this is all equal to 150, which I should make that equal to 0.150 kilometers for good measure. Now I'm going to take that 0.15 and add to it 0.2. So 0.15 plus 0.2, that gives me 0.350 kilometers is equal to 1.414 kilometers squared over hours times U sub SR. So that gives me U sub SR would be 1.414 divided by 0.35. And that gives me USR is equal to 4.04 kilometers per hour. So that should be the velocity in kilometers per hour. And let me think about that. If I do I'm going to check that now. If my velocity really was 4.04 kilometers per hour relative to the river, then 4.04 times, let's say, sine 45 gives me 2.85. That's how fast I'm going to the left, but that's against the 5 kilometer per hour to the right. So I'm going to say minus 5. That gives me 2.14 to the right. And in order to get 2.14 kilometers per hour to the right, a distance of 150 meters, I'm just going to check and see how much time that would be. That time should be 2.14 kilometers per hour. So 0.150 divided by 2.14. That gives me 0.07 hours. Okay, so that's just the amount of time. So now what I'm going to do is see is if that's really the same amount of time it'll take me to go 200 meters when I use 4.04 times cosine. So 4.04 cosine 45. That gives me 2.85 kilometers per hour. And now I'm going to divide 200 by that, or 0.2 by that, divided by 2.8567. And that gives 0.0700 hours as well. So the other one says 0.07009. This one says 0.07001. So I think that is actually a good correct answer. I'm going to put this in just to see. And they want
right.
3 sig figs. Yes, that was correct. So any questions on that? I know when I started off one way, what I did was correct, but I was sort of muddying the waters a little bit. So I'm certainly open to explaining it a little better if you so desire. Anybody have any questions? Anything specific that's bothering you about that? Everybody seems okay. Actually, let me put up the chat just in case somebody's talking to me. Okay. Yeah, we're going over chapter 3, Richard.
I have a quick question.
Okay.
The homework, it says it's due tomorrow at 12:59 a.m. Is that a typo?
Yeah, that's a mistake. In fact, actually, I'm getting ready to change both of those. I thought I did this Friday, but I'm looking at them now and they're not right at all.
Yeah, because yesterday I was doing the part 1, and it says I was late, and I was
yeah,
because it
yeah,
says
that's
due
definitely
Sunday, and I was like, am I late?
what I'm going to do is I'm changing the part 1. I'm going to make that do, let's say, actually, I'm going to make that one due and part 2 due on the 17th. And I'll make the conceptual due on the 17th as well. And
Is all the homework going to be due at 12 a.m.?
At 11:59 p.m. is what it's supposed to be, and I'm changing that now too. I don't know why or how this all happened, but it makes me want to get angry and punch a baby.
Wait, so the chapter 3 that's due tomorrow?
No, it was. Now I've changed it.
When is it due?
So now all of them are due on the 17th.
Okay, thank you. I was a little confused.
And they're all due at 11:59, not 12:59, and p.m., not a.m.
And is there a link in Canvas that we can hit? Because I noticed that there's like a chapter 4 homework in the chapter 2, but there's no chapter 3.
Yes, that was basically a case where I put it up there and then it got erased by something I did later. So yeah, each week's supposed to have it on there. And basically chapter 3, because we didn't finish chapter 3 in a timely fashion, it wouldn't necessarily be appropriate to be in last week. So I'll put it in this week's module. But it's the 17th for part 1, part 2, and conceptual. And that'll push 4 back. I doubt we're going to get to 4 this week and actually literally finish 4. So I'm going to push homework 4 instead of being the 17th, which is, is what it was. I'm going to put it to the 19th for right now, just to see if we can do that. If we can, I'll change it again later. So I got that fixed, and I managed to change
still due tomorrow?
What's that now?
Is our like test or quiz still due tomorrow?
Yeah, I think you still have a test date. Let me double check those dates too while we're at it. So I'm going back to my modules and I've got test one and well, actually test two I didn't open up yet for you guys, but test one's open. And I think that is due tomorrow, which is just on chapters 1 and 2, so that shouldn't be a problem. Yeah, September 12th is when that's due. That's the practice test 1 and practice test and the actual test 1. So yeah, they're both due tomorrow at 11:59 p.m. Okay, any questions on that? All right, so the main trick I did with this problem we were talking about with the swimming across the river is I made use of the fact that when you're talking about the velocity relative to the Earth, then the velocity in the x direction is in fact the u sub SR, which we didn't know, that's what we're trying to solve for, times the sine of 45 degrees. And that has to be subtracted from the 5 kilometers per hour because the velocity of the river is 5 kilometers per hour to the right. And we're fighting that at USR times times the sine of 45. So that's where that 5 kilometers minus USR square root 2 over 2 came from. And velocity times time gives us distance. So that's why I could say parentheses, that quantity times time gives me 150 meters. Now, at the same time, I needed that same period of time, the time required for me to go the 150 meters from C to B, in other words, parallel to C to B. I needed to cross the river in that same amount of time. So that allowed me to take the USR times the cosine of 45 degrees, which is square root 2 over 2, multiply that by T, and that gives me the 200 meters. And then I solved that one for the y direction. I solved that for T and plugged it in the one for the x direction. And that allowed me to determine what the ultimate speed was. Does that make sense to everyone? All right, so it's not a trivial problem, and in fact, it's kind of weird to make it want to come up at B instead of A. In fact, I thought I remembered the problem wanting us to get to C instead of B, but that was not the case. Of course, if you did do that, that would be a lot easier because C, if you wanted to actually swim across the river from A to C, notice you just have to have that A component or that velocity at A. I need that that X component, which goes to the left. I need that to just cancel out the 5 kilometers per hour, which means that USR times times sine 45 would give me 5 kilometers per hour. And that would be enough to figure out the whole thing because then you could just solve for the magnitude. But in this case, the way they were asking was a much more challenging problem. So does everybody follow that? Anybody have any follow-up questions on it? All right, and yeah, none of those assignments are ever supposed to be 12:59 a.m. That's always supposed to be 11:59 p.m. I don't know how it switched. I'll try to change them one by one. So far, I've just gotten chapters 3 and 4 fixed. I think chapters 1 and 2 were already okay, but somehow those got changed. So anybody have any other homework questions before I start into getting us on the same page with doing vectors? All right, I'm looking at this. Okay, so last time I didn't do much. I was just talking about magnitudes, directions, that kind of thing. So let me give you a little bit of an intro. First off, vectors are things that have magnitude and direction. And if you want to, quote unquote, model a vector, one thing you can use to model a vector is an actual arrow. So vectors exist independent of coordinate systems, but often coordinate systems are what help us better specify them. So I can just draw a vector in space. For instance, I can draw a vector like this. And I call that vector A. Now, vectors are normally written as uppercase letters with an arrow over the symbol. And the reason being is the arrow over the symbol lets you know that, oh, this is a vector quantity, not a scalar quantity. Now, as I said, vectors exist without coordinate systems, but we can also make any coordinate system we wish and then represent that vector relative to that coordinate system. So what we would do is we might have a vector A, say, that is, I don't know, let's say 50.0 newtons. And let's say that's 50.0 newtons at 36.86 degrees, or 36.87 degrees. Now, notice how I wrote that. I wrote a magnitude, and then I just wrote the symbol at, and then wrote a degree. The rule is if someone says a vector is at such and such an angle and do not give any more qualifiers like south or north or compass heading or west of south or anything like that, then you're supposed to interpret that 36.87 as being in standard position as you learned in trig, which means a positive angle would be measured counterclockwise from the positive x-axis. So in this case, we're saying this angle right here is 36.87 degrees. Now, this quantity right here is called the magnitude. And magnitudes technically always have to be positive. Okay, magnitude of a vector is always positive. Now, the components can actually have negative and positive magnitudes because they are actually specifying a direction. So when you say has a negative x component, you're really not saying the magnitude of the x component is negative. You're saying the x component has this value that represents its length, but it points to the left, so we're going to put a negative there. So that's something to keep in mind. Another way to specify this vector, though, is we could, for instance, say, well, let's imagine a shadow cast on the x-axis right here. Then this vector would be considered the x component. And notice I actually put a vector over it, so it's actually a vector all by itself. And in fact, that vector is supposed to be 50.0 newtons. Now, here's the key. Until you get really strong, what you want to do when you have a vector in a drawing like this is you want to write out what sine and cosine are. So I'm going to say the sine of 36.87 degrees. That's some old horse. That's the way I remember it. You might remember it as some sine, O for opposite, and H for hypotenuse. So the opposite is the a sub y, which we'll draw in a second. And the hypotenuse is the 50.0 newtons. And I really should have made that second zero a little bigger, but anyways, here we are. Okay, and now, again, we're trying to learn as we go. So we're going to do the next step, which is say cosine of 36.87 degrees. That's came a hopping for me, our cosine, adjacent, hypotenuse. The adjacent is a sub x, and the hypotenuse, of course, is again 50.0 newtons. So what I can tell you is the x component has to be 50 newtons times the cosine of 36.87 degrees. And since it points to the positive x direction, there's this neat little thing we can use. It's called a unit vector. And a unit vector means a vector that is exactly 1 unit long, not 1 meter, not 1 inch, not 1 Newton. Okay, what you do to get a unit vector is you find a vector and then you divide it by its magnitude, which means whatever units it had, you're going to divide it by those units, so it'll have no units. And in fact, the vector that points in the positive x direction is called the I hat vector. So I can express a sub x by just writing that. Now it's actually a vector because I got that little I hat over there. Also in physics and most of math, when you have a hat symbol over something like that, and you are in the context of talking about vectors, then that little hat means it's a unit vector, meaning its length is one unit, not 1 meter, not 1 Newton or anything like that. Now, the other vector, I can either draw it straight up at the head of a sub x, or I can draw it back here on the axis. I've got it a little crowded right now, so I'm going to draw it back here on the axis instead. So right now, I'm going to imagine a shadow cast on the y-axis right here. And this vector is going to be called a sub y vector. And in fact, from the trip that we took by writing the sines and the cosines down, we can now see that the a sub y is going to be 50.0 newtons times the sine of 36.87 degrees. And again, there happens to be a unit vector that points in the y direction. That unit vector is called j hat. So that's actually complete. I've written the entire vector as a vector now, and it's unambiguous that it's a vector. Notice the left-hand side has a vector symbol and the right-hand side has a vector. You're never supposed to have, for instance, A with a little vector over it equal to something without a vector or a hat over it. Now I can go ahead and do the math. I suspect you guys know exactly what this will be because this is the famous 3-4-5 triangle. So in fact, this is going to be 40.0 newtons in the I hat direction. Or excuse me, that one's going to be 30. Yeah, that one's going to be 30. Sorry about that. I was talking about how easy it was, and then I screwed up. And then this one, of course, is going to be the sine of 36.87. If I do that, sine of 36.87, that's 0.6, and I multiply it by 50. And that one gives me, I was right the first time. Are y'all calculating this with me, or are y'all just sort of writing down what I say? Well, this would be a great time for y'all to catch me and keep from making mistakes. So what I have here just on the side, so y'all understand what I was talking about, is there exists a 3-4-5 triangle. And the way it's supposed to work is, for instance, this is the 1, 2, 3, 4. And this is the 1, 2, 3. So this side could be 3. Notice it's 3 squares. And this side could be 4. And then this side right here is going to be 5. And if you take the inverse tangent of 3/4, you get 36.87 degrees. And in fact, if you wanted to do this one, you'd do 90 minus 36.87, and that'd be 53.13 degrees. So we can clearly see that the hypotenuse is a multiple of 50. Specifically, it's 10 times 50. So the y component should have been the 30, which is where I screwed up. I wasn't paying close enough attention. But the y component should be the 30, which would be 30.0 newtons j hat, and the x component would be 40, and that would be in the I hat direction. Any questions on that? So that's another way you go ahead. Go ahead, Richard. I'm sorry, I missed it.
I got 39.9. Is that still okay? Or do I get 40?
Yeah, basically, if you put in a 36.87, that allows you to, what you think would be rounded to 4 sig figs, but the 50 only gives you 3. And at least when I do it, when I calculate it, 3 sig figs gives me basically the 40.0 or 39.99 or 98, and that rounds to 40. So yeah. And in fact, you can save yourself some trouble if you happen to remember those special triangles. And the special triangles, you just saw the 3-4-5 triangle. There's another one that is equal legs. So this one be 1, this one be 1. And since those two are equal, you know this angle is 45 degrees. And this would be the square root of 2, which is approximately 1.414. So that's another triangle. And then there's another triangle, which is like the square root of 3. For this side, that's about 1.73. Let me get a couple extra digits on that just to be safe. 732.1. Okay. And then you could do 1.00 here. And this angle right here is the small angle, which is 30 degrees. And this turns out to be 2.00. And of course, if we wanted to know this angle, this is the 60 degrees. So those are the 3 special triangles that we often use. And I use those mainly to keep from having to do calculator work. But you can see if I'm not paying attention, I can easily make a mistake, as can you. So it's really helpful when you guys are doing the calculations along with me so you can catch me making mistakes. So that's what a vector looks like. And I did something kind of weird here. I didn't really state it, but basically for me to take a force, which is what, Newton's measure is a unit of force. So when I said vector A is 50 Newtons, I'm taking a force and I'm drawing it on paper. There's technically no way you can really represent a Newton on paper, but you can make up sort of a fake scale if you want. And your scale might be something along the lines of, you could say 1.00 centimeters on paper equals 10.0 Newtons. So that's the scale, and you can use it just like we did in chapter 1 with unit conversions. That means you can write it as 1.00 centimeters, and you can call that OP over 10.0 Newtons. Or you can say 10.0 Newtons over 1.00 centimeters OP again. So whichever number you have, like if you have the paper measurement in centimeters, you multiply it by that right one. But if you have the Newtons, then you multiply that by the left one, and that converts it to paper. Okay, so that's sort of the way you can do it. And you can do that always with a vector. And if you do it very meticulously, like use a very thin leaded mechanical pencil, use a good protractor, be very careful marking the right lengths and the right angles, and maybe even use graph paper, then you can work out all these vector problems by hand with just sort of drafting techniques, and usually get within 1 to 2% error. If you do a kind of shoddy job, you might get as high as 5 to 10% error, but that's about it. If you actually do it with AutoCAD, you can get 0% error. And I will tell you, any of you interested in going into engineering, or the construction side of engineering, or mechanical side of engineering, AutoCAD allows you can actually go to the company that makes AutoCAD, and they will allow you, I think it's a 3 or 4 year license while you're in school. You just have to sign up and give them your school email address, and they'll let you download AutoCAD, and it'll run for 4 years for free. And that's, tens of thousands of dollars worth of cash. Somebody said 3 years, so that might be different than what it used to be, or I misremembered. But yeah, that's something wonderful. So you can use CAD right now, even if you didn't necessarily want to pay for it. All right, so that's one thing, is vectors can be thought of as arrows, and then the length, which will be some number of centimeters or inches or something like that on paper. You can make up a scale like I did here, and that allows you to convert it to a real number that might actually be represented by a vector. And even though it's sort of nonsensical, there's no way a centimeter can equal a number of newtons or a number of meters per second, but still you can make it work mathematically. So that's one thing to know. Another thing to know is if you have a vector, let's say you have this vector right here. Let's call that vector B. If you take that vector and multiply it by 2, then that is a vector that is twice as long as vector B. but exactly parallel to it. So when you multiply a scalar by a vector, if the scalar is bigger than 1, it makes it bigger, but doesn't change the direction. And if it's smaller than 1, it makes it smaller, and again, doesn't change the direction, assuming the scalar is a constant. If, for instance, I wanted to draw 1/2 b, then that would look just like this. Okay, notice how all three of those vectors are parallel. Now, if I wanted to draw negative b, which is the same thing as -1 times b, then all I do is reverse the direction. So when you multiply by a negative number, you flip the direction by 180 degrees. And again, if the number is bigger than 1, you make it bigger. If the number is smaller than 1, you make it smaller. So we can see, for instance, here, this is -2b. And this is -1/2 b. And if you use the idea that b is equal to some x component, that's just a scalar b sub x times I hat plus some y component times j hat, and you might even have a three-dimensional vector, in which case you'd say times b sub z k hat, then I think it's pretty obvious what 2b is. 2b means you're just going to distribute that 2, and those I hats, j hats, and k hat, which looks sort of like a x, y, or z, that's exactly how they're supposed to behave, meaning only like terms can be added. So this one's going to become 2b x I hat plus 2b y j hat plus 2b z k hat. And of course, if you did a -2, it would be a negative in front of each of those terms. Does that make sense to everyone? So these unit vectors are supposed to make it so easy that in principle, if someone gives you vectors in unit vector notation, the I hat, j hat, k hat stuff, and by the way, you can also write it as x hat, y hat, and z hat, that's acceptable. But if they give them to you in that form, you don't have to even draw a diagram to know how to add them or subtract them or anything. So that's another useful aspect of it. Let me now show you something. There's ways you can add vectors. So for instance, we can do head to tail. So head to tail vectors would mean something like this. Let's draw this vector A. And then at the end of vector A, let's draw vector B. Now, that A didn't turn out as well as I liked it. It kind of aggravated me a little bit. So there's my A vector. Now you could imagine, for instance, this little dot at the left end of A, that could be like your front door. And maybe you were going to walk straight out your front door and go straight to the road, but you looked and saw, I don't know, your cat or your dog or something a little bit down the road. So you took a diagonal path off your front porch to go catch with your dog over here at this dot. Well, as soon as you got there, the dog took off running, and then you walked along the sidewalk, which is parallel to the road, some distance that's shown by B, and you finally caught your dog right there at that dot. Well, if that's the case, then you can draw a vector from your initial position to your final position, and lo and behold, that vector is really what you get when you add the first displacement vector A to the second displacement vector B. So A plus B, often called the resultant R, is graphically done like I just showed you there. There's the word I'm saying, resultant. So if you have two vectors that are head to tail, notice the head of A is at the tail of B. Then you draw a vector from the tail of the first to the head of the last. And to be honest with you, A plus B is equal to B plus A. So even that doesn't matter. So it doesn't have to be from the tail of the first to the head of the last, but it should be from the loose tail to the loose end. And if it's 3 vectors, you still draw it from the loose tail to the loose end. If it's 25 vectors, you still draw it from the loose tail to loose end. Does that make sense to everyone, how you add those vectors? Now there's another way, and this is called tail to tail. And in this case, you could have, for instance, a vector like this would be vector A, and you could have like this would be vector B. Those vectors are tail to tail. And the way you add vectors tail to tail is you complete the parallelogram. Okay, so I'm going to draw something that looks just like B, but I'm going to draw it at the tail of, or at the head of A. It looks like B goes up 2 while it goes to the right 3. So I'm going to go right to here, basically. That's the parallel to B part. And A looks like it goes to the right 1 as it goes up 3. So A is going to be like this. So now I can see that this part is parallel to A, and this part is parallel to B. Okay. So the sum of the two is in fact drawn from the common tail to the diametrically, to the opposite corner. Like this. And I don't know why I'm drawing all my vectors crooked today, but that's not cool and I'm not liking it. Let's see if I can do it a better way. Let's do this. Yeah, that looks better. Okay, and this vector is A, this vector is A plus B, also equal to the resultant. So you see how you add vectors that are head to tail and how you add vectors that are tail to tail? Any questions on that? Now there's another problem too. For instance, A minus B, you might remember this from pre-algebra, but A minus B is defined to be A plus the opposite of B. Well, this comes in kind of handy here. So let's start off by drawing our vectors head to tail, or excuse me, yeah, head to tail. So I'm going to draw vector A. It's going to go right here. That's vector A. And then I'm going to draw vector B. And that's right there. Okay. Now, when you have vectors that are head to tail, notice how easy it is to add. So I'm going to say right here that this is easy to add. Now, when you go to do subtraction and they're head to tail, it's not so easy, because what this A minus B is defined to be the opposite of B, or A plus the opposite of B, really means you have to take A, or excuse me, you have to take B and create its opposite, which is this guy right here, negative B. Now that's particularly problematic because this now makes me 2 vectors that are tail to, or head to head, and we haven't learned anything like that, but we can still do our parallelogram rule. So I can pull B down here and notice that it's actually 1, 2, 3, 4 spaces long. So it would be right there. There's negative B. And now you can see my vectors are now in head to tail orientation. So I just have to draw from the tail of the first to the head of the last, which would be this guy. So this vector right here is A minus B. Any questions on that? So in this case, you'd say hard to subtract, meaning you have multiple steps you have to do. Now let's look at when they're tail to tail. So when they're tail to tail, I'm going to say this guy goes up and over 3. So that's my A vector. And my B vector is going to go up 2, but over 3 as well. 1, 2, 3. So that's going to be like this. So there's my B vector. Now, negative B turns out to be that guy. And now you can see that this is A minus B. Notice that when they were tail to tail, it was hard to add. You had to complete the parallelogram. But when they're tail to tail, it's easy to subtract. So hopefully that will help you a little bit in remembering which way to go. Anybody have any questions on that?
I have a question.
Yes.
When you're doing head to tail, if you're subtracting, like you said, it's hard to subtract, but if you're subtracting a B, couldn't you just switch the direction of the vector and then just draw the line and that would still be the resultant vector?
So yeah, that's what I did. You said when they were head to tail, right?
Yeah, like the tip to tail method, yeah.
Yeah. So in that bottom left corner, that's what I did is I turned B negative, but when I turned B negative, that put B where its head was bumping into the head of A. I haven't given you anything to do with that. So that's why I said, quote unquote, it's hard. But all I really did was after I got that, I slid the B down and made it slide down so that you don't stretch it because that would change its magnitude, and so you don't twist it because that would change its direction. But I just slid it down so that its head was at the tail of A, and then I knew I could just draw it from the tail of negative B to the head of A. So yeah, that's pretty much what I think that's more or less what you saw, and I was just trying to restate it in sort of the same words that I did. Does that make sense?
Yeah, that makes sense.
Okay. Yeah, so that's really the trick. Another thing you can see, of course, if you were to draw B first at the in the head to tail diagram that you have, the first one, that little blue dot, if you drew B first horizontal and then drew A at the head of that, you'd see that B plus A is the same thing as A plus B. So that's a common thing with vectors is A plus B is equal to B plus A. They commute. It's another way of saying it. It's also the same thing as saying they're abelian, some fancy mathematical term, which I kind of like just because it's a weird mathematical term. But anyways, so now that we have that, what I want to do is show you one really good, robust addition of vectors problem. So I'm going to take, let's say A vector is equal to 50.0 newtons at, and I'm actually going to use the same one I already did, 36.87 degrees. Actually, I did this in class today and I mistakenly used the wrong angle, so stuff didn't come out so nice and neat as it was supposed to. Now, what I'm going to try to do is I'm going to try to express these 4 vectors in the various ways that they can actually be expressed in physics. So we express vectors a lot of different ways, and I want to make sure you guys have been experienced with all of them. So I'm going to start off by drawing my little coordinate system here, and this is going to be the x-axis, which also corresponds to east, which is 90 degrees on a compass. Okay, this is going to be my y-axis, but that corresponds to north, which is 0 degrees on a compass. And then, of course, this will be south, and this will be west. So I've got A is equal to 50 newtons at 36.87 degrees. I'm going to say that B vector, in this case, I am going to say it is 200 newtons at, let's say, 60 degrees NOW. Now that means north of west. So I'm going to show you what that means in a second. We're also going to have vector C, which is going to be, in this case, let's say it's 104, yeah, 141.4 newtons at, in this case, I'm going to say compass heading of 225 degrees. And then I'm going to say D, that's going to be, that's going to be, yeah, I think I'll do this. I'll say it's, let's say it is 250 newtons at negative 51, or excuse me, 53.13 degrees. Okay, so I've sort of expressed all the different ways they can be expressed. I'm going to draw them quickly. I'm not going to worry too much about scale because you can see I've got as small as 50, which is pretty small, and then 200, which is 4 times as big, and 250, which is, 5 times as big. So I'm going to try to do 36.87. I'm going to draw vector A. Vector A is going to be about 36.87 degrees, and it's going to be about 50 newtons. So I'll say that's A right there. And notice I just said at 36.87 degrees. So that means counterclockwise as measured from the positive x-axis. So I'll put that little arrow there. Then B was 200 newtons. And that's in 60 degrees north of west, which literally would be way the heck up here. Okay, now this angle is supposed to be 60.0 degrees, and that's vector B. Okay, notice north of west means that I go 60 degrees north of what the west direction is. If I had said 30 degrees west of north, that would be acceptable too, except this part right here would be 30 degrees, which is obviously the same thing. Any questions on that part? Now for C, C is supposed to be 225 degrees of the compass heading. Well, if it points due north, it's 0. If it points due east, it's 90. If it points due south, it's 180. 225 is another 45 past that. So I'm going to try to split the uprights here. And in this case, I'm going to make it 141, which is maybe that long. Okay. Obviously, I'm not taking much time to draw it to scale. You should draw it to scale, especially when you, as many times as you can, for probably maybe the first 5 to 10 vectors you add. This is going to be vector C. And in fact, this angle right here is 225 degrees, but this angle right here is 45. And that's what I'm going to be using. And then finally, I get to vector D, which is negative 53.13. And in fact, it's quite long. So I'm going to draw it like this. And that's vector D. And this angle right here is 53.13. And notice it went clockwise from the positive x-axis. That's what a negative angle means. So now that I have that, what I'm going to do is I'm going to interpret all of these vectors as having positive and negative components. So for instance, A, if you cast a shadow on the x-axis, that x component is positive, and that y component is positive. If you cast a shadow on B, that x component is in fact supposed to be negative, and that y component is supposed to be positive, like that. Doing the same thing with C, we see that both the x and the y components are negative. And then finally, if we do it with D, I can see the x component is going to be positive, and I can see the y component is in fact going to be negative. Okay. So what I can do is I can start writing. You could make a table, for instance, if you want. You could also put them by I hat, J hat, and K hat, stuff like that. Here's a table that I often make for my students. I definitely make it with the algebra-based class, but I hardly ever make it with the calculus-based class. So you put a column for your vector. You put a column for your magnitude. You put a column for your direction. And then you put a column for x component. And then a column for your y component. Now, if it's a three-dimensional vector, you can go ahead and do that as well. But you don't have to in this case because it's just two-dimensional. So there's my vector A. Its magnitude is 50.0 newtons. And you might even stick a newton in parentheses up there so you don't have to write the unit every time. This one's at 36.87. So you can just put it as the standard form. If you convert it to the standard form, then that would allow you some freedom to blindly use some formulas, but I recommend you do not do that. Okay. Now, what's going to go in here is I'm going to take 50.0 newtons, and I'm going to realize that that over A sub y is equal to the sine of 36.87, and A sub x over 50.0 newtons is equal to cosine of 36.87 degrees. So in this case, I'm going to take the x component. I'm just going to take 50 newtons, and I'm going to multiply it by the cosine 36.87. And that gives me 40, and it's positive. Okay. And then I'm going to take my 50 times sine 36.87, and that gives me my positive 30.0 newtons, like that. Notice by taking the small angle, in this case, it was the only angle, but by taking that small angle, the trig function is never going to give me a sine. I have to decide the sine, and that's what I want you to do. I don't want you relying on taking the standard angle as measured counterclockwise from the positive x-axis, so this sine function will spit out a negative, because there's times when that doesn't work properly, and unless you know all those little details, it's not worth it. And it's way better for you to physically think about which way the x-axis is pointing versus which way your x component is pointing. So when we see, for instance, on B, I'm going to say B has a magnitude of 200 newtons. It has a direction of 60 degrees north of west. So we might actually call that 120 degrees. That would be acceptable. And I'm going to say 200 times. Now in this place, the x component is definitely negative, so I'm going to force a negative right there. And I'm going to say 60 times, or excuse me, 200 times cosine 60. And that gives me negative 100 newtons. And now the y component is going to be positive, so I'm going to force that there. So I'll put the positive there. Now I'm going to say 200 times the sine of 60. And that gives me 173.2 newtons. Now I can do C, and C has a magnitude 141.4 newtons. And it has a direction, technically speaking, that's 45 on the other side too. So I could call that 225. And that happens to be the same as the compass heading, even though it's entirely differently measured. So in this case, I'm going to say 141.4, and I'm going to multiply it by the cosine of 45. And that would give me the y component as I have the 45 drawn now. But if I have the 45 over here, then the cosine would give me the x component. So I'm going to say times cosine 45. Luckily, cosine and sine of 45 are both the same thing. And in this case, they're both negative. So it's going to be 100 newtons negative. And then this one will be negative 100 newtons as well. And that one comes from 141.4 times the sine of 45, which gives me, again, about 100. I got 99.98. which to one decimal place is clearly 100. Now I'm finally going to do D. Now D has a magnitude 250 newtons. Now that one's technically at negative 53.13 degrees. So that's kind of nice. I can just write it in the way it is. The x component is in fact positive. So I'm going to put a positive here. And I have to get it by multiplying multiplying 250 times the cosine of 53.13. And that gives me, in fact, 150 newtons. Notice the hypotenuse is not an easy factor of 5. In fact, you have to multiply 5 times 50 to get 250. So you know that the 3 is going to be multiplied by 50. That's what the 150 is. And 4 is going to have to be multiplied by 50. So this other one should give me 200. So for that one, I'm going to say 250 times the sine of 53.13. And that gives me, of course, this one's a negative 200 newtons. Now I can draw a line to represent sort of the addition line. And when I do that, I got to put an X down here so no one makes a goofy mistake of trying to add magnitudes and components, but I will add them right here. And I'm going to say, here's the resultant vector, A plus B plus C plus D. So what I do is I'm going to say 40 minus 100 minus 100 plus 150. And that gives me negative 10. Now that's technically only 2 sig figs because I had a single extra sig fig after the decimal place on that top number, but I had none on the bottom. So that's what happens with that one. Now this one, I'm going to say 30 plus 173.2 plus minus 100. And then minus 200. And this one gives me negative 96.8. And of course, I'm only supposed to have a sig fig up to the decimal place because obviously I didn't have decimal places in the 100s. So now I can just write if I wanted to, I could write the resultant vector with my IJK notation. But the rule of thumb is if I give you the vectors in magnitude and direction format, then you should spit it back in that format. If I give it to you in IJK, you should spit it back in that. But in all cases, you should follow the instructions. So right now I can say R is equal to A plus B plus C plus D, but that's equal to negative 10.0 newtons I hat minus 96.8. Notice I'm underlining the non-significant digits, newtons, and that's the J hat direction. But that's really not the way I'm supposed to do it. So I'm going to draw a coordinate system over here to show you how you do it. There's our X coordinate. There's our Y axis. I have a vector that's negative 10 newtons to the left. And then I have a vector that's negative 96 newtons downward. Okay. So what that means, actually, that's not very clear what that means. Let me make this look a little better. Okay. What this means is the resultant vector is that vector. Okay. And, oops. And this angle right here is going to be the angle I call phi, and that'll come in handy. So I'm going to say, I'm going to take the quadratic formula and I'll compute negative 10.0 newtons squared negative 10.0 newtons squared, and then negative 96.8 newtons squared, and 10 squared plus 96.8 squared. Okay, so 96.8 squared, by the way, gives you 9,370, but it only has 2 sig figs, so it's only good to the nearest 100. And 100 squared has 2 sig figs, so it's only good to the nearest tens. So when I add those two, I get 9,300 or 470.24, which only has 2 sig figs. And then I take the square root of that. So I'm taking the square root 9470.24. And that's actually in newtons squared, by the way. So I'll take that, and that gives me 97.3 newtons. So the magnitude is 97.3 newtons. Notice I carried 1 extra sig fig, and now the phi is equal to the tangent inverse of 96.8 over 10. Notice how I didn't write any signs in there. I don't want that. That's going to cause problems. So I'm going to say tangent inverse 96.8 divided by 10, close parentheses. That gives me 0.1. Whoa. 9 point. Yeah, I did that right. Oh, no wonder I hit tangent instead of tangent inverse. Tangent inverse 96.8 divided by 10. That gives me 84.1 degrees. So I'm going to say this is at 84.1 degrees, let's say south of west. That would work. I could also say 180 plus 80 would be 264.1 degrees. That's just standard notation. I could do that way. I could also say it's a compass heading of 180 plus 5.9. So 185.9. So compass heading 185.9 degrees. All of those are different ways. And that's it. Time's up. I just wanted to make sure you guys knew how to add a series of vectors. In this case, I actually did 4 vectors. That method I showed you with the head to tail and the tail to tail, those work too. You just take 2 at a time. Any first 2 that you want, get a result, and then use the head to tail or the tail to tail method to add that resultant to the 3rd vector, and then do that again. Use that resultant to add to the 4th vector, and you can just keep on doing that over and over again graphically to get your vector. But this is the actual answer. It should be about 97.3 newtons or 97 newtons at about 84 degrees south of west. Anybody have any questions? All right, well, next time we're going to do nothing but projectile motion stuff, and that'll be finishing chapter 3. So you guys are done. We've already set the due date back on the chapter 3 homework. So make sure you get that. Make sure you knock out test 1. That's, due tomorrow, tomorrow at 11:59 p.m. So make sure you get that done. You're free to go. I'm waiting for the last person to leave, and then I'll split.
Oh.
Do you have a question, Richard?
Oh, no, I ain't had no question. I was actually pressed the unmute button.
No problem. Michael, RCR, anybody else? Anybody have any questions? Now, you don't have to use this table. In fact, like I said, I never show it to my calculus-based physics students. But sometimes when it's online, it's just more efficient to show them a table. But the main thing is, once you can write a vector as, some number times I hat plus some number times J hat plus some number times K hat, that's already essentially a table. You're just adding the I hat components together to get a net I hat component. You're adding the Y hats together to get a net Y hat component, and so on. So anybody else? Zoom user. How about RCR?
Hey, this is Eric Franson
gotcha.
from your what is it, 202 class.
202 class.
Anyways, apologies for the name. That's my machine name. I'm not
No
sure why I
problem.
didn't put my name in.
Did you have a question, Eric?
Yes, but in my class, I guess. So I'm intending to wait for everybody else to finish.
Oh, that's cool. We only have one more student who's listed currently as Zoom user. I suspect they might be from
It's me,
class.
Tiffany from your normal
Okay.
202.
Gotcha.
Oh,
Hey,
hey.
Tiffany. So we got 202 students. So yeah, go for it. Ask me your questions.
What day are all the tests due?
Let me double check so I don't mistakenly say something. So I was just talking to them about the 241 test, but I'm going to pull up your 202, and I think I've got test 1 and test 2 posted for you guys. So let me check and see exactly what those dates are. I sent out a couple emails over the weekend regarding that. So I'm looking right now. Practice test 1 is due on the 13th, and test 1 is due on the 13th. So you have until 11:59 p.m. on the 13th for test 1. And then test 2, which covers chapters 18 and 19, you have until September 18th at 11:59 p.m. for those. Or excuse me, for that test and that practice test.
Okay, that's so much better.
Yeah.
I spent a couple hours getting my Pearson corrected with a subscription, so I got that taken care of. I sent you an email because I was worried about it.
Gotcha. Yeah, I've been
It's now done.
communicating a little bit with our Pearson rep. I don't know what's going on with that, but it's not it made me ill, but hopefully everybody looks like they're getting it worked out now.
Did you get an email from the people at school that do time extensions? I forget what department that is.
Oh yes, that was I did get, yes. Yeah, I did get an email on that. So what I will do is I've got to look that up, double check names and all that stuff, which obviously you know what it is. And I will do the extensions per requested, but thanks for reminding me that.
Understood. Yeah, I don't want to start it with its times until it's ready for me.
Yeah, exactly. That's cool. Yeah, I'm looking at the email right now. I think I got that like Thursday afternoon, or might have been Friday, but I thought it was Thursday afternoon because I remembered seeing those, and I was like, I gotta go back and look at them, and then I didn't, because that's just how awesome I am.
It happens. It's okay. I was trying to look for when these tests were due. It's not in Canvas. Anyways.
Yeah, they're listed in Canvas, but they're really little gray things at the bottom. And then the homeworks that are done on MyLab and Mastering, even if Canvas shows them, they're not necessarily right. So never pay attention to the Canvas dates. Always pay attention to the dates when you click on MyLab and Mastering. Your name was Eric, right?
This is correct.
Yes. Gosh, I've had 84,000 emails since then, evidently, but now I'm finally finding it. Okay. Yeah,
that is astonishing.
Anything else? Anybody else have any questions?
I do.
Go for it, Tiffany.
Okay, so you probably saw my email or not. I couldn't work on the practice test because there was no questions that would pop up. It just had the time running. I'm like, how am I supposed to practice?
Oh wait, that's a good time to text me immediately. When that happens, what's happened is I've put questions in, and then like it started acting like it didn't recognize the test bank. So I did have a student email me that in one of the classes. I don't think it was 202 though, and they told me that was a problem. And I looked, I opened it and fixed it. But is that still showing it that way right now?
I can click into, because it's the one you can take multiple times, so I wasn't too concerned.
Gotcha.
I'm gonna see real quick right now. I'm sitting in my car. I just got out of work late, so let me see. Yeah, it still pops up with no questions in there.
Okay, yeah, so that's completely worthless. So even what I'm doing right here now, sitting this, is not very helpful. That's cool. And is that the practice test or is that the test test?
That's the practice test.
Jeez,
if it was the test, I would have had a heart attack.
Yeah, it's never supposed to do that. It's just, okay, so I'm looking at practice test 1. It says it's got 100 points. That's usually the indicator that it worked, but clearly it's not working. Oh yes, that's nice. I see exactly 0 questions.
Yeah, I was like,
that's super helpful. All right, let me fix that real quick, which is not as fun as you might think. I'm gonna do edit. I'm gonna do edit. It's gonna go really slow because it can. Yep, there it is. It definitely just pooped the bed. So there's 2, there's 5 points each. This is chapter 16 and 17. So I got to look for chapter 16 questions. You can go ahead and answer any, ask me any material questions if you want while I'm doing this. This isn't actually too terribly hard.
Oh, perfect, because I did have a question about one of the homework assignments.
Go for it.
So in my bank, it was question number 15.
Mm-hmm.
In chapter 17, I was struggle busting hard. After a couple hours, I gave up, but it's basically, the question is, how much energy is stored by the electric field between 2 square plates? They're 8.3 centimeters on the side, separated by 1.9 millimeter air gap.
Which question is this?
Number 15 on chapter 17.
Thank you.
Okay, so there's a formula that says the energy stored, it calls it U, and the energy stored is the square of the electric field times, I want to say it's E squared times epsilon 0. That's the formula they're supposed to use, but that's the energy per unit volume. So then you have to multiply it by the separation distance and then times the area of the plates. That's how that one's done.
Oh, that's where I was, because I'm like, I know I need to have both the numbers, but I wasn't sure how to incorporate it. That makes sense though, now that you say that.
Yeah, it's just a plug, supposedly a plug and chug formula, so hopefully that'll be pretty straightforward for you. But yeah, it looks kind of daunting when you don't have any idea what it is. You're like, oh, I don't know what
Because
they're
I was
talking about.
reading the book and I was like, I see exactly where it should be, and then they had multiple formulas. And then the other thing that was driving me nuts is it has NC instead of MC. You know what I mean? So I was like,
Oh,
do I have to convert it?
yeah, so nanocoulombs, yeah, that's 10 to the
Right.
negative ninth. So when you have a lowercase n, that's 10 to the negative ninth.
Let me write that down.
So yeah, that makes it fun.
And I'm like, I know it's a different conversion, and I was looking online, but then I'm like, I need to step away.
Well, did y'all find the equation that I was referring to just now?
I can't see the book because I don't have it in. Actually, I have it in my trunk, but I mean, hold on a moment. Let me run to my trunk.
I was just wanting to make sure you could find it in your book because I was using
Yeah.
my memory. Okay, I now have fixed practice test 1. So thank you for letting me know that. I'll fix practice test 2 as well, and all that good stuff. Do you have another question, Eric, while you're waiting for that one?
Yes. Do you have an equation sheet for these 2 chapters or for the class?
Do I have a what sheet?
An equation sheet for.
Oh, no, I'm in the process of still making it, but I have not succeeded yet. So I would definitely go through chapter 16 and look at all the equations that have a little parenthesis and then the chapter number dash and then a number close parenthesis. Any equation that has that in chapter 16, I'd write it down. Then do the same thing for chapter 17, same thing for 18, and just keep it going throughout the semester. That'll help you a lot.
Okay. Yeah, it seems like there are 4 big ones, which are dealing with U and F, and the difference is field and points.
Okay.
Okay, but yeah, that's what I was doing, is going through the chapter. It's
gotcha. Yeah, so that's really is the process you go through just to write those down. Once you've gotten to the point where you are doing homeworks, you'll be able to see which ones you use that often, and you might be able to drop a few. But in my estimation, it's usually better to have an extra symbol or 2 than it is to be missing one. So I usually just leave them all. And I don't have any limits to the number of problems you can put or the number of equations you can put on there. So that shouldn't be a problem.
Is that for the in-person test? Yeah.
Yes.
Okay, thank you.
No problem.
Okay, I think I found the equation. Is it the half epsilon
Yes.
e to the squared AD?
Yes. Area times distance. Yep, that's the one.
Do we need the big E? We just need the A and the D, right?
Yeah, the E is the electric field strength. So for instance, for a parallel plate capacitor, which you just found, the electric field is sigma, the charge per unit area, divided by epsilon naught. So you end up getting, actually, I can show you that on there.
What's the name of this equation?
It's
Still
the
15.
energy stored in the electric field. Do you have a number on that one?
Number 15.
So yeah, it's 1/2 epsilon 0 E squared. That's the formula you're supposed to use for this. But it's also times A times D. So the electric field for a parallel plate capacitor, which also say is PPC, is sigma over epsilon naught. So you're going to get 1/2 epsilon 0 sigma squared epsilon 0 squared A D. Obviously, one of those epsilon zeros is going to cancel out down here, and you end up getting sigma squared A times D over 2 epsilon 0. And basically what we're talking about here is, here's your 2 parallel plates. this is your distance D between them. And this right here is your area A. So that's what goes in for the A. And the sigma, by the way, you can say sigma, that's actually the charge divided by the area. So you might even be able to simplify it more by saying Q squared over 2A squared epsilon 0 AD. Now you can see one of these A's cancel out and you get ultimately Q squared times D over 2A epsilon naught. So that should be the simplified version. If they just gave you the amount of charge that was stored on one of the plates, that would be the Q. If they gave you the separation distance, that would be the D. If they gave you the area in like square centimeters, you need to convert that to square meters, but put it in there. And then the epsilon 0 is the 8.85 times 10 to the negative 12.
Okay. Yep. I've got that down. Yep. I think that's it. Well, thank you.
You're welcome. Hopefully that helped.
Oh yeah. If not, I'll let you know tomorrow. Okay.
Okay, no problem. How about you, Eric? I did find your sheet. I was just looking at that, Eric. I had to make sure exactly what the email said so I can adjust the test accordingly. So I'm now in that.
Very well, that's fantastic news.
Yes, so I can take care of that, no problem. Do you remember if it was time and a half or double time?
It was double time.
It was double. Okay, no problem. That's just easier. Right now I'm trying to do 15 things at once and I'm not that good at that. And I'm going to do that for your practice test too, so that'll just help you.
Thank you.
No problem.
Well, awesome. Well, thank you so much. That was pretty much my question. I'm going to do this one question when I get home later on and then do my test. So thank you so much.
No problem. Thank you for coming. And Tiffany, make sure, like I said, if you ever run into that problem, that's definitely one that I want you guys to text me on my cell phone immediately, because I don't want that. I don't want y'all to have to waste any time doing that. So that's my screw up. It normally works, but sometimes it just doesn't. And right now I got to go check all of them, but I will.
Okay. No, thank you so much. I'll text you in the future then for something like that.
Thank you. Appreciate it.
You got it. Thanks for your time.
Thank you. You're welcome. Eric, do you have any more questions? We got plenty
Yeah,
of time here if you need any.
Yes, just about the equation that's on there. It is U. U is meaning
Total energy. So that's the energy, in this case, it happens to be the energy stored in the electric field, because it's sort of like it's almost like if you're out in the ocean, there's a spot in the ocean that has some built up energy, and you can tell it because you look to your right, you look to your left, and the ocean's flat. But then as soon as that part of the ocean gets to you, it lifts you up. It's got potential energy in it because clearly there's a wave there, and that wave can lift you up. So that's sort of the same thing happens when you put charges on one side, on one plate, and charges on another plate. That makes an area where an electric field can be established. And in order for that to give things energy, that electric field must have energy. So the U is really the total amount of energy stored in the electric field between the plates.
Yeah, I think a lot of these story problems throw me off because they're so strange. I get the comparison to gravity where you need two things to equal the third. It's difficult to know which equation or what to do with these problems.
Yeah, so a big part, especially the beginning of the semester in the 202 course, a big part is learning not only the equations, but what each symbol means, and specifically what units it has, because sometimes that's your savior to figure out what is this quantity that they gave me. If they gave me it and it's some number in newtons per coulomb, ideally you'd want to say, oh, that's electric field. Or if they gave it to you in volts per meter, hopefully you'd know that's electric field again, just in a different type of unit. But if it's something like amps, then you need to know its current, and that would be represented by the symbol I. So a lot of the beginning parts of a calculus-based physics or an algebra-based physics course is really not only figuring out the equations, but figuring out what each symbol means and what units that symbol normally has.
Okay.
So yeah, that is a big problem. And you can, in principle, you're supposed to be able to get it from the reading, but I know I've been a student before, so I am well aware of how hard it is to read the textbooks. Just try
A lot of
taking
it is
it
implied.
smaller bites.
Yeah, a little bit will be implied within the story problem.
Yeah, exactly.
I had one more thing. What was the name of this equation? It was PPC.
Oh, I called it parallel plate capacitor. So that's the energy stored in a parallel plate capacitor.
Energy stored. So it'd be like I'm trying to compare it to organize my formulas. If it would be electric force, electric potential energy.
It's like in joules.
Field.
It should be measured in joules.
It's a joules. Okay, thank you for your time. I think I'll get off of here.
No problem. I'm fixing the test right now. I've got both practice tests fixed for you, and I'm doing the regular test next. So,
all right, I'm going to take both of the online tests were due on the 13th, correct? I'm going to wait until that day.
Yeah, the 13th is test 1 and the 18th is test 2.
Okay, I'm going to.
More time.
Yeah, I'm going to need it. All right, thank you.
All right, good luck, Eric. Have a good one.
Good evening.
Bye. What you playing over there, baby?